we begin with a very promising title. Now, before we start, I want you guys to know that I hold you personally responsible for interrupting a very important debugging session for this third assignment. So I'm here, but half of me is desperately aching to go back to debugging. But unfortunately, that will have to wait. Oh yeah, we can erase stuff. So before we begin the actual lecture, I did change the schedule for two reasons. The first one is to allow the third-year students to participate in lectures as they need, and the second one is to add another hour to the end of each lecture to do a discussion of how you and I implemented the assignments. All right. So if you have any questions, if you're stuck, then the third hour is going to be a mixed laboratory and lecture. So I'll show you my solution, I'll discuss it, and you'll be able to ask me questions as in a regular working class. Before we begin with this exciting topic, I would like to discuss the difference between world and local spaces. This is something that I kind of give for granted. Who does? Oh, no one. Okay, alright. So this refresher is needed. Now, usually, what quantities do we track in a body that we want to draw? A drawable entity, a physical body, whatever. Two things that track their status as a logical status and as it is going to be drawn. Two quantities. Go. Yes. Shout it. Come on, I heard something that sounded like
Position.
The position, of course. So this is going to be something like a vector 3. Let's say also emitters. This is the position, right? And what else?
Orientation.
And the orientation. All right. Now the orientation is some kind of, let's say, a rotation, whether it's a matrix or it's a quaternion. So let's just stay vague and let's say this is a rotation, and let's call it rot or whatever we want. Rotation, orientation, they're close enough. All right. Now, what happens when we have a point, a vertex in the body, and we want to find its position in world space? So let's say we have a cube, and the cube originally is here. This is the origin, the center of the cube is the origin, and we have this vertex here, which is 1, 1, 1. Okay? How do we find the position of this vertex? Let's call it R in world space.
Multiply the world matrix with the position.
Alright, so you multiply the world matrix by its position. How do you derive the world matrix?
It's normally the orientation of the world is the first 3 axes, and the last one is the translation.
And the last one is the translation. Now, here we're dealing with, let's say, purer rotations and transformations than we usually do in graphics. So this is a 3 by 3 matrix, if it's a matrix, so this just is the rotation. What you have described is exactly doing the following. You transform R by the rotation, and then you add the position. Is it clear what this process is? So if the cube has to be drawn here, what we're saying basically is that this point here, let's call it R prime, you find it by first rotating R by the rotation matrix. So R prime is going to end up here, actually a bit lower, and then you transform R prime by adding the position. So in this case you multiply by the rotation, and in this case you increment by the position. Is the idea clear enough? First you rotate the object, yes?
What's a world matrix?
The world matrix is a single 4 by 4 matrix that contains the rotation and the position together. But it's a 4 by 4 matrix, and the last column is the translation.
So it has nothing to do with the actual world?
No, it doesn't.
Okay.
Absolutely. The world matrix is just a matrix that incorporates the rotational and translational transformation that you apply to a point to find its position in world space. So this is in local space, or body space, or object space, because it's the position of the object, not in the world. So just when it was created, Alright? Whereas here we have the position in the world, the actual position that the point will take when you draw it, when you do physics with it, whatever. Its actual current position. Is this distinction clear? Who finds it clear? Alright. That's close enough. One piece of advice. If this isn't clear, think about this long and hard. This is going to pop out everywhere for the next 3 years if you understand it, 12 years if you don't. Alright? Okay, so let's do the opposite now. Let's say we have this point because a bullet has hit the cube at this position. So the collision detection system tells us in the world this is where you have been hit. Now we want to know the original point that was hit relative to the cube itself. How do we go back? Well, so we know that r prime is equal to this because that's how we compute r prime. But let's say you have r prime and you know that the body has this rotation and this position. You want to find the original position. How do you do that?
Multiplied with the inverted.
Okay, the inverse of the word matrix, of course. But how do you do this in concrete here? Because the word matrix is nothing more than these two quantities. Did you have a question?
No.
Oh, alright. So, let's do this by steps. R prime is equal to, let's call the rotation just big R for ease of writing, plus P. Okay? Now, we want to find R, so first thing we subtract P from both sides, right? So, R prime minus P is equal to big R times R. Still following? Okay. Now, we want to remove the rotation matrix. So we multiply both sides by the inverse rotation matrix. So, R to the minus 1 multiplied by R prime minus P is equal to small r. Okay? Fortunately for us, inversion of a matrix is an expensive process, but if R is a rotation matrix, then we can transpose it and we get the inverse. Okay? This is just a piece of convenience that makes our computations much, much faster. Okay? Now, for a live demonstration, I am the object in worlds in local space, alright? And this is R, small r, okay? Alright? Now, my rotation is going to be a U rotation, so around my vertical axis by 90 degrees. So I'll keep it here. And my translation is going to be a translation of 1 step right and 1 step forward. Okay? So, what do I have to do? First,
You have to turn 90 degrees first.
First, I turn 90 degrees. Why first? Because first, you multiply by the rotation matrix. So this is what happens when I multiply by the rotation matrix. Now I'm not a rigid body, so I can turn my neck and keep looking. Now, I have to add the position. And the position means 1 step, well, to the original right, and 1 step to the original front. And that's where I am. Okay? Is this clear? Now, every rotation I do happens around the original point. So, as you well can imagine, if I start by translating and then I rotate, now the rotation is going to be around the center. So the rotation is going to be something, well, I'm going to end up there. Alright? I'm going to end up in the wrong place because I also rotated the position. Okay? Now let's do the opposite. So I'm here, I'm correctly rotated. This is R prime now. This is the transformated R. Right? So what do? We want to find out the original point. First, I subtract the position. So first I go back to the original position. Then I multiply by the inverse rotation. The inverse rotation does the inverse of the rotation, so it rotates me against what I rotated originally. And so we end up back to the point like this. Is this clear? Now the intuition for this thing is very, very strong. So become very comfortable with this. Just recognize these formulas. I mean, recognize how you go from the original point to the transform point, and how you go from the transform point to the original point. Yes?
I was doing this in code and I just set the rotation to 0 in my matrix.
A rotation by 0.
No, to 0.
To 0? Say again.
So I was making matrices.
Yes.
And so I could set to set rotation to a specific angle.
Yes.
So I took my cube, I put it in the origin, rotated it to 0, 0, 0, made a new matrix, applied it. So why would you do something with an inverse matrix?
That's to go from the transform point into the original point.
I just subtracted my current position.
You cannot just subtract the current position, because if the object is rotating, subtracting the current position will give you the original point, but not counting the fact that the new point was rotated.
So, and then I put the rotations to 0.
But no, you cannot just, if you put the rotation to 0, okay, so if your original cube is not rotated, then the rotation matrix is going to be the identity, so there's no rotation. And of course, when you don't have any rotation, then you can just subtract the position.
Yeah. So
But if the object is rotated, which is going to be most of the cases in an actual game,
I just unrotated it.
unrotating means multiplying by the inverse rotation matrix.
That's strange.
No, it isn't.
Well.
So, first of all, the problem is that, you know, this point here, this point has a certain set of coordinates, which is going to be something like, I don't know, 25 minus 7. Alright? If you
So
subtract,
I draw my vertices, I draw them, yeah, they have their own position, and when I draw them, I add the position of the cube.
of course, you add the position of the cube.
Yeah.
So when you draw them, you just are ignoring this bit here.
Well,
I think what he means is that everything he does is in local space except for the point when he draws. Then he adds the position. I think that's what he does.
yeah.
Yeah, okay. But let's say your physics system tells you that there's been a collision. So this is the head of your character. So it's not exactly the best character ever, but this is the head of the character. And you know that the character was, I don't know, crouching, diving, whatever, and you hit him here, alright? And this is a critical point, whatever. You need to find out exactly what the original point was, but this is rotated. You see that it's rotating, it's tilted and forward. So if I just tell you, there's a hit at 25 minus 7, this is what your physics engine, this is what your collision system tells you. There's a collision at 25 minus 7. So the question is, how do you do this? How do you go from this point here? You're not told you have hit vertex of the vertex number 27, then you know vertex number 27 is this one. You just know the collision is at this position here. You just know the position of the collision. And you need to find the position of that collision in the original body.
I don't have collision check. So.
Yeah, alright, clearly. So when you're just rendering, the only thing that interests you is this. Is how you build the world matrix, or is how you go from the original point to the transform point to draw it on the screen. But the biggest problems arise when you have to go in the other direction. That's it. So for example, you may need to apply a force to the object to push it away from a certain point, and that point is the point where the user has clicked. And that point you can only find it by going from the world position back into the local space position. Because this is where the force application actually happens. This is it. Just learn it. This is not my invention, so I can actually vouch for it with the strength of thousands of scientists. So can you feel them? They're clamoring to pass knowledge on. Oh my. Okay. Alright, so now, well, fortunately there's a recordings for this, so you can go, but I'll probably make some slides of it. Now, let's talk a bit about about differential equations. Well, differential equations are something that is usually considered a very, very hard topic, and the reason for that is that they are a very, very hard topic, but they are unfortunately unescapable in physics. Now, the point of differential equations is to find numerical solutions to some complex problem with derivatives and time. We'll see how to set up the numerical solutions, what we need to be able to track, what we need to be able to know. We'll see the simplest method, which is Euler's method, and then we'll see how you can potentially derive more sophisticated methods, and then we'll derive a method which we can kind of assume that it's the best, alright? But it's not necessarily. Now, a differential equation has the form x dot is equal to f of x of t. What this really means is rather simple. So we have x, which is the state of the system. You can imagine it as an array of float. The state of this system, for example, would be position and rotation. Alright? And you can somehow, through a function f, compute the derivative with respect to time of x. So in our case here, we have the position, we have the rotation, and we have the rotation. What we do is we usually add a vector in meters per second, which is the velocity, and another vector in radiances per second, which is the angular velocity, which we also call omega, usually. Alright? So, the function f that gives us the derivative is going to be something that returns us the velocity and the angular velocity, which are the derivatives with respect to time of the position and the rotation respectively. Alright? Is this clear? So, f of, let's say this is our rigid body. Then f of a rigid body, r, is going to be equal to just the pair r dot velocity, r dot angular velocity. Alright? Very simple. So this we can compute easily. So we can compute easily the first derivative of a system. The first derivative always means velocity. Velocity of some kind, the rate of change of something. Okay. Now, of course, though, we're missing something. We also have the velocity and angular velocity, of which we need to be able to compute the derivative. But those are rather simple. Those are the acceleration, so it's going to be r dot f divided by the mass, and r dot tau, which is the torque, the angular acceleration divided by the inertia tensor. Something that's very important here is that the force and the torque are set from the outside. They actually come externally. So they are not really part of the state. They are the external state. They come from the interactions from the other bodies. So this is the derivatives with respect to time of a rigid body. Alright? We can compute this. This is not even a computation technically. We're just stating the fact that these are derivatives. And we want to know the new position, the new rotation, the new velocity, the new angular velocity, given that we can compute their changes with respect to time. Differential equations, the theory of differential equations gives us a general purpose toolbox for dealing with differential equations in general. So not even knowing what the shape of f is. As long as we can compute f in some manner, then we're fine. And we can apply a differential equation method to actually solve this. So once again, x is the state of our rigid bodies, and f gives us the derivative of the state with respect to time. So velocity, acceleration, angular velocity, and torque. So how the various quantities change. The velocity represents the change of what quantity?
Position.
The position. The acceleration represents the change of what quantity?
Velocity.
The velocity. The angular velocity? Rotation. And the torque?
Change of angular velocity.
The change of angular velocity. Alright? So these are very simple things. Oh, yeah, there it is. Now remember that the angular velocity, actually, we have to compute we have to take the columns of r and cross them with omega from the previous lecture. Yes?
Why is torque used to, yeah, exactly. Why is torque compared with angular acceleration here? I mean, instead of angular acceleration, use torque before?
So, okay, it's a charming question. We have two options here. Either you track as additional quantities. So either you track the velocity and the acceleration, but then when you are added the force, then the the velocity and the force and you will integrate by doing something like the velocity is incremented by the force divided by the mass multiplied by the delta time, right? Or you track the linear momentum p, which is equal to the velocity multiplied by the mass. This is just the quantity that we track. And so you can do that the linear momentum is incremented by just the force multiplied by the delta time. But if you go this way, then you'll have to increment the position. Oh, let's call the position x. It makes my life a bit easier. X is incremented by p divided by m multiplied by the delta time. Alright? So you see, at some point I have to do a division by m. Either I do it in the force to get the acceleration, or I don't do it in the force, I just integrate the linear momentum, and then when I add the linear momentum to the position, I have to divide by the mass. If the linear momentum is equal to velocity times mass, and if I divide the linear momentum by the velocity, I get by the mass, I obviously get the velocity. Alright? So the point is, where do we want to do this division? It doesn't matter at all. You can store the force, you can work with the velocity, or you can work with linear momentum. The very same thing happens for the angular momentum. So the angular for the angular momentum and angular velocity. So we can either track the angular velocity, which is then going to be incremented by the angular acceleration multiplied by delta time, and the angular acceleration is going to be the torque multiplied by the inverse inertia tensor multiplied by delta time. The inertia tensor is the equivalent of the mass with the rotation. So we multiply by -1, and we have the inverse matrix, which is exactly a division. Alright? Or we have L, which is the angular momentum, and we increment L by the torque multiplied by delta time, but then when we increment the rotation matrix, we will use something that comes from L multiplied by I-1 multiplied by delta time. Here's the, we use the T and B crossed with W from the previous lecture. Alright? But in any case, the thing we do is the very same. So the question becomes, in this case, for the rotation, where do you use the inverse inertia tensor? Do you use it for the angular acceleration, or do you postpone until you have to compute the rotation? And if you take a look at how many computations you'll have to do, the number is exactly the same. So it doesn't matter.
Yeah, no, we're just a little confusing. Go back one slide, please.
There?
You compare the angular velocity with velocity and then torque with acceleration, which is...
Oh yes, that is a typo, of course. And here you would have, so acceleration force, and here should read angular acceleration slash torque.
Yeah.
Yes, absolutely. Now, this may seem like a trivial thing. It is not. Symmetry in physics is absolutely crucial. Alright? So for example, the first implementation for me of the first assignment, I had the force I was applying to the cube was something like 1,000, whereas the torque I was applying to the cube was 0.1. That cannot possibly be right. Symmetry has to be there. If it's the same cube, then it's the same amount of torque that you apply as a force, as a magnitude. Otherwise, something else is wrong. Okay? So this is absolutely fundamental. Learn to spot these little unclean and asymmetric things. They're very important. Okay, good. So, alright, now of course the ideal solution would be, alright, but just give me the new state at time t. Isn't there some super cool mathematical way to just say the game is after 5 seconds, what's the current position and rotation etc. of the entities? And just knowing a closed form solution, like, I don't know, position dot x squared plus something else. No, there isn't. These things happen only for the simplest of problems, and ours, as usual, doesn't qualify. So we just we look for an approximate solution, and since we know how to compute f, knowing how to compute f means that we can compute the so-called field of slopes of x. So x is the state of the rigid body, and you can imagine it as kind of a marble, right? A marble in a landscape. And f represents where the landscape goes, so how the marble moves, how the marble transforms. And so here is a slope field. You can see that these are the directions of the f function at every point. So the squares contain the possible positions of x. So these are the possible states. Of course, in our case, the state is not 2D, is much more because we also have the rotation. And what we do is we start from one point and we try to follow the various slopes. We start at x0 and we take a bunch of discrete steps. So here, you start here and you take a step in the direction of f and you keep doing that on and on. But we take discrete steps, so we actually make mistakes. We may jump too much in one direction, whereas in the continuous case, if delta time was, imagine, as small as possible, almost 0, then we would be able to follow the thing perfectly. So Euler's method actually just takes big discrete steps along the slope. That's it. So we know we are currently at time t. We want to end up, or to know the state at time t plus h, where h is our delta time. So what we do, we take the current state and we simply add the delta time multiplied by the first derivative. And the first derivative is the bunch of velocities. So it is what we compute with the function f. Alright? So it is the set of velocities. And alright, you'll hear a lot of things about Euler's method. Well, they're usually true, but it may actually be acceptable in some cases. So do not dismiss the simplicity and the performance of this method, because it really does very few computations. And yes, it is reasonable. I mean, it is mathematically sound. And if your frame rate is good enough, and if you really don't need particular precision, it is simple to code, it's simple to debug, it's very fast to run, so actually consider it. Right? For the assignments, I'm actually trying to see how far I can go, and up to the third assignment, so up to collision response, it seems to be working rather well for a few objects. So it may actually be that it works. But otherwise, if it doesn't work, and it may well not work, especially at low frame rates, then it is absolutely infeasible. There's no way to make it work as it is. The kind of errors you get, imagine if you have a rather big time step, or if the f function changes a lot, then you take a first big step like this, and you end up definitely where you shouldn't be. You end up here, and then you go here, and this is once again very wrong, and then you take another big step and so on, whereas the right movement should have been this. You see? So you have to imagine that the difference is that the position of your object is wrong. The rotation of your object is wrong. So the object is rotating in a direction that it shouldn't be rotated towards, or it's in a position where it shouldn't be. And the bigger the step, the bigger the error. Okay? So with a relatively small time step, you see here, for example, there's a small time step. If the steps are small, then the errors may be acceptable. If the steps are averagely big steps, then yeah, you still make some error, but if the steps are long, then you'll make gigantic errors, and then it simply becomes infeasible. Okay, so and the method is inaccurate because it may jump from one trajectory to another, so you just go to some other rail of the object, and it's not stable. That is, it may increase the energy of the state, so it may bounce and it may even explode. So for some things, especially when you have springs, then the energy of the system increases. So the springs, instead of damping, they keep blowing up, and at some point you have the object bouncing from one side of the screen to another until you get another number, and then nothing works anymore. Okay, and this is the example. So imagine the f are a series of concentric circles, but if we take a long enough step in the direction of the tangent of the circle, then we end up in another circle, and then another circle, and then another circle. You see the error? You go to one trajectory to another, so an object that should just move in a circle doesn't move in a circle. It moves in an outward spiral. You can actually easily do this yourselves if you want. And the instability is that, imagine your object should go here to the middle and then go forward, like falling down a hill and then following the bottom of the valley. But if you take two long steps, you'll end up on the other side of the hill, then on the other side, then on the other side, and you may actually end up even outside the system itself. Alright? So these things may actually happen, and yeah, visualizing them in 3, 4, 5, 6D, which is our case, is a bit more difficult, but this is still what happens. So what you have to imagine is that your velocity and your rotation, for example, they should stop, but, or they should diminish, but actually they just increase and they blow up. Alright, now, how do we derive a sophisticated solution for a differential equation? Well, as you may remember, Taylor series. Who remembers Taylor series? Oh, come on, guys. Any function can be expressed as the sum of all its derivatives. So we know the function at the value of the system at time t, and we want to know the system at time t plus h, so a bit in the future, where the amount of future time is h. So we take xt and we increment it by h multiplied by the first derivative. This makes sense, right? But then we have the second derivative as well, and it contributes, so we multiply by the second derivative by h squared divided by 2, and so on, and every derivative, the nth derivative, is multiplied by h to the n divided by n factorial. This is an approximation that if you, well, this is not really an approximation, this is an expression of a function. So the original function is correctly expressed as the sum of all its derivatives. Now, how many derivatives does a function have? Infinite, alright? Okay, so the idea is that every derivative is a function in itself that describes a kind of movement, and you take all these movements together, you sum them, and you get the behavior of the original function. Knowing this, we can truncate this summation to approximate the original function. And all differential equation solvers are more or less based on this technique. So you say, okay, let's ignore until this point, and we make work with what we have. And indeed, Euler's method, well, you know that this was the original expansion, and you just say, okay, we stop here. Can you see it? Very simple. You just stop there. And how do you figure a more accurate method is going to work?
Use more derivatives.
You stop, well, for example, there. Alright? So let's see how we can derive the midpoint method. So we take another step. Just one more. So now we have the second derivative. And the problem is that we don't know the second derivative, we only know the first derivative. Right? We don't know as a function, don't look. We don't know as a function how the acceleration is going to change. That is given by the user. That's external. We cannot say what the acceleration is going to be in the future because the user may or may not decide to interact, or there may or may not be a collision, whatever. So what we do, we simply approximate with Euler's method itself. We don't care about the steps. We really don't. We approximate the second derivative with the first derivative f, which we know. We know how to compute the first derivative, right? So we can use that with Euler's method to compute the second. Indeed, yes, we approximate f itself with Euler's method. There is a bit of algebra. Yes, this is the algebra. If you want to check it out, do so. It's not very hard, but it's not so important. But what really happens in the end is that yes, we can derive that x, that the second derivative of x is equal to, is equal to this big function here, approximated with Euler's method. So very important is that this function, this value here, comes only from f, and f, right? So we don't need anything else. We're using the information we have about f to approximate. We sample it twice, and we use it to approximate f prime, or x second, which is the same. Of course, there is a downside to this. For a step of this method, well, we're doing quite a lot of computation. So the end result is that with the midpoint method, when we want to compute x of t plus h, then we compute f once here, as we did with Euler's method, but then we compute f 1, 2, 3 more times. Alright, so we compute, oh no, wait a second, this one is equal to this one, so 2 more times. And depending on how heavy computing the velocity and angular velocity is, well, this is more expensive. So this method is already almost 3 times as expensive as the original one. All right. Oh yes, this is a visual way of seeing it. So first you take half a step. So this would be the step that Euler would take, and here you actually take the half point, you do the derivative there, and then you get something that's marginally more precise. Okay, the more terms we have to approximate, the more evaluations of f we'll have to make. So the heavier the system is going to be. But we're talking about 2 times, 3 times, 6 times heavier per entity. So that's the reason why, if you can get away with Euler's method, there's a decent case in terms of performance to do so. The so-called best numerical method is Runge-Kutta 4. Okay, it has this long formula, which you should all be familiar with. You have seen this in MA4, right?
Yeah.
Who hasn't? Say, raise your hand.
Well, I wasn't in there, so.
Yeah, alright. But the point is, this is something you just copy, but the point is, you keep computing f at various points, 1, 2, 3, and 4, and then you average all of them.
I see RK4,
Yes.
and I noticed it also in your slides about the assignments. It also listed RK2, and when I was looking for
RK2 is this one.
that's midpoint. Midpoint
Yes.
is RK2.
And
What?
you know why it's called 2?
Be-
Because it computes the second derivative.
Right. So
Whereas this computes the...
is there also an RK1 and 3, or is that
1 is Euler,
Euler and then
and 3 we ignore.
Three you ignore.
3 is kind of the
Okay.
stepchild of derivative of differential equation solvers. You can do it
yeah, okay.
if you want. No one talks about it. It's like the crazy uncle at the family parties. All right.
That's good.
So you see, what we do is actually very simple. So this is a step of Euler. This is a step, well, let's say almost of the midpoint method. This is another step forward, and this is another step again. And then we average them. We just average. So these are a bunch of possible first derivatives. We just average them. You can see it, and we give more weight to the middle ones because they're the most accurate. And so what we're doing is we're computing first this derivative, this is k1, then this other one which is k2, then this other one which is k3, and then this other one which is k4. We take all of these, we average 1/6, 1/3, 1/3, 1/6, which add to 1 of course, because it's an average, and that is the acceleration that we pick. And this method is surprisingly accurate. That's the reason why, especially in game physics, you can consider this to be the perfect method. So the one that's going to give you the best results in terms of precision. Now, a very nice question is, why don't we use our RK5 or 6? Now we're already doing a load of computation, so why not go even more? RK5, RK6, RK7, RK12, why not? Right? Is it more precise or not? What do you think?
It's not worth it.
Why? So, what do you think? Is it too heavy? Is it? It is too heavy. Is it more precise though?
Probably.
Who says yes? Who says no?
I kind of already read the slides.
Oh, come on, then you're out. Who read the slides already? You did.
Only two about
No,
this part,
you can't answer. Come on, that's cheating. Yeah, but alright. But if no one knows, then
But I like the explanation though.
yeah, I like this very much actually. So the point is that what kind of information do we have? We can compute the first derivative, right? Can we compute the second derivative? No, we can't compute it. We can approximate it, right? So here, can we compute the third derivative? No, we're approximating that. From what? From the approximation of the second derivative. What about the fourth derivative? Alright, you see where this is going? Actually, what you're doing is just approximating the higher order derivatives with the first derivative only so far. After a while, it is the same information that you're just inputting into the system again, alright? But you don't know the final answer. So at some point, you can't really just keep pretending that you have higher order derivatives. You don't have them. So at some point, you cannot approximate anymore. And you start approximating stuff that doesn't exist. So the system actually breaks down after a while. So if you take a simple function like the sine or the cosine and you keep adding new approximations, you'll see that at first it gets very nice, you get a curve that really looks like the sine, and then after a while it starts oscillating like crazy because you're using wrong information, and wrong information actually puts in tiny oscillations which are far worse than what you think you may gain from a higher approximation. This is it. But the point is, differential equations are not that hard. We're always relying on... Come on. We're always
Almost.
relying on Taylor expansion, and we approximate this. We can compute easily the first derivative. We have everything. We have the velocities and we have the forces, and then we try to approximate some of the higher order derivatives. All right. So this was 2. Yeah, this was easy.
Why are
Now
you
let's go
running
to
Dutch?
3. Sorry?
Why are you running Dutch?
Why shouldn't I?
Well, inclusive.
Because I can.
Okay.
Wait, what?
I don't
Do you
even.
even understand everything?
I don't even run Dutch. Yeah.
No, because come on, seriously, my daughter is learning Dutch in Kinderdagverblijf, so I need to.
Yeah.
Seriously, I need to be able to talk to my daughter. Oh, damn, stupid thing.
Well, no matter what language you're in, that's still called a crash.
Alright. Okay, now this other lecture is, yeah, it's another one of a series of lectures. Oh, come on. It's another one in a series of lectures that I consider to be very important for the understanding of game physics, and which, yes, may be perceived as something a bit on the theoretical side. So my apologies for this. Once again, there's only one way to fake physics in game, which is doing physics. So, sorry. So here's a bit more physics. Now, we talk about integration and rotation. So we have a rotation, matrix, or quaternion. How do we work? How do you integrate a matrix? Then we'll talk about the inertia tensor a bit. Then we'll talk about how you normalize a rotation matrix. And this is a very, very, very important topic. So pay close attention, because being able to normalize a rotation matrix means that you can also, for example, derive a rotation matrix from just 2 of its columns, and opens up a bunch of possibilities. Then we'll talk a bit about quaternions and how you integrate a quaternion into the system. Now, the time derivative of a quaternion and using quaternions are the second part of assignment 1. So if you have assignment 1 working with rotation matrices, then get it working with quaternions as well, and see if you can spot the difference. Oh, by the way, who's working on the assignments? Who's got the first assignment working so far? All right, that's close enough. Very good. The deadline is this Friday at, say, midnight. All right. This Friday, the deadline for assignment 1.
We need to upload it somewhere.
I need to upload it on my Dropbox, on my shared Dropbox.
yes.
folder.
That's not gonna
Yes,
work.
absolutely, which is on Nestle. Yes, please upload it.
Can we get a link to the Dropbox?
Sorry, Netschool.
That's cool.
By the way, is this perfectly understood? The assignments are group assignments.
No.
So, the assignments are group assignments. I want you guys to program the assignments in groups of 3, 4 maximum, alright? Then write something on the assignment, but the code has to be shared. Write something individually to make sure that you understand the steps, but the assignments should be done in groups. If you really want to do them alone, but please don't. They are hard, very hard. Do not. Come on, this is seriously. If you can get some help, get it. Don't bang your head against this particular wall. It's a
Does it mean 3 people have to hand in the same code?
the same piece of source, but 3 different reports.
Ah, okay.
Short reports, 1 page.
Okay.
Alright, you say, I've implemented this, I've implemented these equations, this is how to translate into code. That's it. The code for the physics assignment is tiny. It's like 50 lines of code for the first assignment, if at all. It's for the physics part, of course. Alright, so, indeed. Now, let's go for, let's discuss a bit the case where the position is a vector. Yeah, let's call it X. The rotation is a matrix. Let's call it R. Instead of the velocity, we track the linear momentum. So this is a vector. Oh, damn. Linear momentum. Oh, yes. Kilograms meters per second. Kilograms meters per second. This is the linear momentum. We call it L. Remember, linear momentum is equal to
Mass times velocity.
mass times velocity. Thank you very much. Alright, so this is exactly the same as tracking the velocity. Alright, so whether we track the velocity or the linear momentum, the very same thing. This is in relation to what I said before for each question. Then we have the angular momentum. Okay, now this I'm probably gonna get wrong. I usually rely on the compiler to tell me if it's right or wrong. And the angular momentum. Oh, wait a second. Yes, sorry. This is not L. This is P. L is the angular momentum. My apologies. Very important. Very careful. Okay. And this is equal to, oh yes, the inverse inertia tensor. We can call it J or I. Everyone calls it either J or I. So I'm moving. There's no ambiguity here. So if you see a big J or a big I, then that's guy. Multiplied by the angular velocity. Oh, sorry. Once again, not inverse. The symmetry always helps. So mass times velocity, J times angular velocity. Okay? This is the state we track. So now we also have, and these are the things that always change. So these are the variables, so to say, of the system. Okay? Now we also have the external, so we need to track the mass. So this is a floating point number in kilograms, and this is the mass. And then we have a matrix, which is J or I, depending on what letter you prefer. Okay? Do these change? No, they don't change. So these are constants. Why don't they change? What do they represent? The mass, obviously. Let's see how heavy the object is, how much mass the object contains. Yes?
The inertia tensor, the other one.
Sorry?
The other one is the inertia tensor, I was going ahead.
Yes, this is the inertia tensor, absolutely. Yeah. So the inertia tensor is a matrix, and it represents the distribution of mass across the shape of the body. Alright? So how mass is distributed over the body. If the body is symmetrical, then you have, for example, a symmetrical J with only a diagonal, the rest is 0. If the body is not symmetrical, then the various entries of the matrix represent a particular direction of rotation and a particular distribution of mass across the geometry. Alright, so at this point, what else do we need to track? A rigid body. Yep.
The force and the torque.
We need to track a force, and the force is going to be in newtons, force, and we also need to track the torque. And the torque is another vector, and I think it's in newtons per meter, and this is the torque. Now, who gives us these? Where do they come from? From the outside. They are externally set quantities. They may be set from input. In assignment 1 that's going to be the case. They may be set from, well, you may have gravity, for example. You may have the solar wind that pushes your ships away. You may have the collision system. The collision system obviously applies forces, okay? But you cannot really compute them from inside the body. So these are indeed externally set. Alright? Good. So, what we need to do now is, we need to integrate the various quantities. So we'll have some function, like update, and if you remember from the end of the last lecture, we need to be able to take the force and the torque and put them where? Where do the force and the torque go? What do they go in update?
Acceleration.
No, these are the acceleration and the angular acceleration. They're just the acceleration and the angular acceleration multiplied by constants. So you don't care. You already have the acceleration. It's here. So these two quantities go into updating the linear momentum and the angular momentum. Alright? So first line of the update function, or however you want to call it, which is clearly going to depend on delta. Oh, wait a second. Which is going to depend on the delta time, which is in seconds. Update is going to start and it's going to, well, increment the linear momentum by the force multiplied by delta time. Alright? Does everyone agree with this step? Okay. Then we do the very same with the angular momentum. So the angular momentum, tau multiplied by delta time. Check the vectors and the units of measure. They have to be correct. Check them, because if you make a mistake, then the physics engine is still going to, well, work in the sense that you'll be able to run the program. So remember to track all this information that I'm writing. So the units of measure are important. The fact that, yes, tau is a vector, so multiplied by a floating point number, you still get a vector. So yes, it makes, you can at least add it here. So keep reasoning on these things. Alright, now we want to increase the position, and the position is going to be, I'm not going to say this myself, so go ahead.
Linear momentum
Yes, linear momentum
times delta time.
times delta time
Divided by mass.
divided by mass. Yes. So, let's see who's right. Linear momentum, kilograms, meters, second. Alright? So, kilograms, meters over seconds divided by kilograms, so we get meters per second. Multiplied by seconds, we get meters. And, oh, the position is in meters, so this is fine. Is this clear? The dimension, this is called dimensional analysis. You make sure that the dimensions that you have are correct. Okay, great. Now, oh, the rotation. Alright, now this is obviously the most problematic one. So what we do, for the moment, let's say we do r dot multiplied by delta time. How did we compute r dot? If you remember from the previous lecture, so let's say that T, N, and B are the columns of R. You extract them. How? Well, you look up the values from the matrix, the columns of the matrix. So first column is T, second column is N, and third column is B, which are the reference axis of the object. If you plot them, if you draw them starting from the center of the object, you get T, N, and B. T, N, and B. Alright? So these are the current axes of the frame of reference of the object, which represent the orientation of the object. Is it clear? Can you imagine? You have a rotation matrix, you just extract its columns. You guys look kind of lost here. Yes?
Is it much easier to do with a quaternion as rotation?
Much easier. Alright, that is absolutely not the term I would use. But yeah, we'll get there. The steps are the exact same, so what changes are 6 lines of code. But yes, we'll get there. Alright, so you take these, you compute the angular velocity, which is going to be L multiplied by the inverse inertia tensor. So J minus 1 multiplied by L. Alright? We're extracting a velocity, so basically we're taking a momentum and dividing by the rotational mass. Okay, now you can compute R dot as the matrix where the columns are the cross product between W and T, W and N, and W and B. Alright? So is this process clear? These are just steps. So you're seeing how much the columns of the matrix are relative vectors to the are vectors in the body. You just see where they would go, and where they would go depends on the angular velocity, and it's perpendicular to where they are and where the angular velocity, the rotation axis, is. Then, well, usually for convenience, we zero the force and the torque because we've applied them. So we wait until the external system sets back a torque and a force into the bodies. Okay? Alright. Oops, I just gave you the solution to assignment 1. This is jokes aside, assignment 1. Of course, if you really want, you can do a Runge-Kutachu or 4 integrator on this. Whereas, well, that's what you have to figure out. I'm not going to go and write this on the whiteboard. Okay, now, there are 2 very big issues. First one is that this value here should be somehow recomputed. So I'll write here, where does J come from? And the only way we have seen is to compute J from every particle that makes up the body. There was a big summation of a big matrix computed from R times L for every R in the body. This would be deadly slow, so this is not doable. So we need to find a way to track the inertia matrix from some value that we compute at the beginning, at the start, and how to track it as the body rotates. And the second problem, very delicate one, is that, well, this process here, what we're doing is we're taking t and we're incrementing it by w cross t multiplied by delta time. Can you see this? So the sum here, what it really does is incrementing every column with some other value, which is a velocity, alright? So we do t plus omega cross t delta time, n plus omega cross n delta time, b plus omega cross b delta time. And we're doing this with Euler's method. So other results going to be very precise? Not exactly. There's going to be some error. And the error is not going to be the same for t, n, and b. So they will get different errors. So now you have that the forward vector has some approximation, but the upward vector has some other approximation, and the right vector has some other approximation again. So what should be a rotation matrix slowly stops being a rotation matrix and starts incorporating some skewing. Okay, so we'll see now how to solve these 2 problems. Now the first one is a body shape issue. So we know J, and it has to represent the tendency of the body to resist rotation, but the body is just moving and rotating. It is not changing shape, because we're talking about a rigid body. So in principle, we should be able to recompute the current value of J from its initial value, which we can compute from the particles or from a closed solution. You'll find on Wikipedia the initial J for plenty of shapes, spheres, cubes, etc. And we apply the rotation somehow. This is actually the whole computation. We know that originally we knew that J was computed like this, where Ri is the position of every point that makes up the body. Alright, just look at the first line. Ignore this. This is just for completeness. If you want to study this, do so. Otherwise, can't really see why you would want to do this, but here's the steps. And the point is that we apply, we know that these positions here, they are rotated by the rotation matrix R. So we go on, and what results is that the new J, the J now, is computed from the initial J, the first one, the one that you downloaded from Wikipedia, multiplied by the rotation matrix and then by the transpose or inverse rotation matrix. So basically what we're doing is we're taking the shape of the body, which has its own distribution of mass, etc., and we're just rotating that with the body itself. So the body is rotated, so obviously its resistance to rotation is going to rotate with the body itself. Alright? Good. And even better, we only use J to the minus 1, so J to the minus 1 is equal to R, again, multiplied by J bodies to the minus 1, so the original one inverted, which we need to compute just once, and then multiplied by the transpose rotation matrix. So, what we're saying is that here, we could, instead of tracking the mass and J, we can, saving some computation. Remember, you may have a lot of bodies, so saving computation is always nice. We don't really need the mass, so we track the inverse mass, and here we track the inverse J. Alright? So instead of dividing by the mass here, we just end up with 3 floating point multiplications, which are, fortunately for us, rather quicker than floating point divisions. So this is better. We're happy about this. And J to the minus 1 is computed from R multiplied by J inverse multiplied by the transpose of R. So this is the moment of inertia in world space for the body rotated with rotation R. Okay? And this step needs to be done. That is the reason why we start with rotation matrices and not quaternions, because quaternions, well, they don't really mix well with the fact that we have matrix. Of course we can use quaternions, but you'll still have to go through a rotation matrix and you'll have the rotation matrix as a temporary value inside your update, because you cannot just do with the quaternion, even though the quaternion has some significant advantages. Are you still following? So this is exactly the update step for a rigid body. Now if you add a force and a torque appropriately from user input, then you actually get, indeed, most of assignment 1. Second problem though is that when we perform this step here, so rotation is obviously the biggest problem that we have in approximating physics. As we keep integrating R, T, N, and B stop being orthonormal with an orthonormal frame, so they stop being perpendicular to each other in pairs. Imagine T drifts a bit towards Y, whereas N drifts a bit towards minus Y. Now, of course, they're not exactly perpendicular to each other anymore, okay? And when you put them in the columns of a new rotation matrix, then no, they're not a rotation matrix anymore. They're a decent approximation of a rotation matrix first that breaks down faster and faster. So if you do nothing and have a very big torque, or you keep pressing the torque button, alright, the object starts spinning and spinning and spinning very, very, very fast, and at some point it's going to start pulsating and then it will just blow up. Try to achieve this result. It's cute. It has to go very fast. Because being very fast is kind of the same as having not exactly, but kind of the same as having a very small time step, a very big time step, because you're doing very long approximations in one frame. And do I really need to say the last line?
It's awesome.
It's awesome, yes, exactly. Tell your producer I have something, an awesome explosion of my models in my body. That could actually be something fun to take pictures of the face. So can we base a game on the errors of physics? Alright. This is the kind of box that you get. So if you start with a box, it is slowly going to be crushed. Alright? And yes, it's even worse than this because it pulsates and moves and you can't see anything more. So we can use the so-called Gram-Schmidt method, which you should use. So we compute a new method. So we start with what we call R hat. This is, so instead of compute, this is not R, this is R hat. Okay? And then this is a temporary value, a temporary matrix. This is close enough to the final matrix, but we need to do something with it before we're actually able to work to work with it. So now we do R equal to ortho normalize of R hat. And wait a second, what did I do? Oh yes. And the orthonormalize process, well, first of all, it normalizes T. So the first thing we know is that all of these vectors, all of the columns of the matrix have to have length equal to 1, because they are axes of a rotation matrix. So they are axes, they have to be long 1. So we divide T hat by y, the length of T, and the resulting vector has length 1. Alright? Who doesn't know why this happens? I actually do, but I'm just freezing. For sport. So this is clear. When you divide a vector by its length, you get a vector that points in the same direction, but which has length 1. This is also called
Normalization.
Normalization. Okay? D3DX vec3 normalize, for example. Okay, then you'll find plenty of libraries that deal with this kind of stuff for you, for graphics. Okay. Then we take the dot product of n hat multiplied by t, by the right t. So t is, let's say, the right t. We accept it, we start from t, and we say, okay, we say this is the tangent. Even though it may have some approximation, at least it's a one length vector. So we can accept it, alright? as a tangent. Then we project n hat over t. So we find how much of n hat can project over t. Now, if they are completely perpendicular, yes?
You said multiply, but are you multiplying or doing the dot product?
How can I multiply two vectors?
Well, you just said you multiply.
And it doesn't make any difference. As I said, the dimensional analysis and the type analysis gives you always the correct answer. I can't really take two vectors and multiply them. There is no multiply operation between two vectors. The only multiply operation that makes sense here is the dot product. So this is something that has to kind of come under your skin. The operations that you can perform are never ambiguous. There's always one operation that you can do. So in this case, when you do the dot product between two vectors, or of course it's not correct to say multiply, but there is no doubt whatsoever I cannot possibly mean anything besides dot product, because they are two vectors. And because here I'm clearly doing a multiplication of n by the dot product, and the result needs to be a vector. So if you try to do something like a type checking of the types of your symbols, then you will always get to the correct answer. Learn to do this, because this is very important. So you project n hat over t. So you find how much of n is parallel to t. Now n and t need to be perpendicular. So you remove the projection. And then you normalize the new vector. And then you recompute b as t cross n. Because now you have t and n, and you can just compute a b vector, which is perpendicular to both of them, with a cross product. Alright, so what's happening, and this is the reason why we actually wonder, can we do something better? And you can almost hear the answer, quaternions, right? There's lots of computation which is useless. So every frame, or every, say, 5-10 frames. But even worse, the matrix representation is very redundant. So we're doing a lot of computation, and this lot of computation is done on a representation which is redundant. Why is it redundant? What values of those three are we using to compute t, n, and b?
T and n.
T and n. T hat and n hat. Are we using b hat?
No.
No.
But are we tracking stuff with b hat? Oh yes, we are. So this is a bunch of computations over b which are absolutely, utterly pointless. Okay? But you see, here we compute the new b, we sum it to the previous b multiplied by delta time, but then we just don't use it. Alright? We just ignore it. And we ignore it for a very good reason. It really has to be perpendicular to both of them. So there's no other way. You can't say, okay, but what if I use them? No, you cannot. You must do it like this. But there's no other way to derive a vector that's perpendicular to them. Wherever b hat is at this point is absolutely irrelevant. Okay, so what we really need is a single rotation around an axis. Because this is the only quantity we're tracking. We just need a single rotation. The most compact way possible to track a rotation. And fortunately for n, we don't want any degrees of freedom, additional degrees of freedom. Now we are tracking a rotation matrix, but a matrix could store a lot more transformations. Could it have a scale? It could have a scale, for example, right? It's a matrix. Can it have a scale?
Yeah.
Yes. Okay. It can have a change of axis. It can mirror things. It can do plenty of transformations. So we are tracking 9 numbers which represent a wealth, an infinity of possible transformations, most of which are not rotations. So it's like saying you have this awesome thing that can do amazing stuff, but you just use it for rotations. Alright? This is wasteful. And it adds a bunch of numbers and a bunch of computations that are just adding noise to what we're doing. So this is not improving the situation. And if we can just track a single rotation, in the most compact and most compressed possible manner, then we will have less values that can make mistakes, and we'll have less need for normalization. So our computations on less values, which can only store a rotation, presumably will be more precise because we have less ways for the matrix to store wrong values. So, alright, now, just try to get the intuition out of this. The point is, you know very easily, do you know this matrix here?
Z rotation.
This is a rotation. This is a rotation around the z-axis. Alright? The simplest rotation possible. This is a rotation essentially in 2D. Alright? Now you'll say, what does this have to do with anything, right? Oh, and by the way, we can call it like this. Cosine minus sine, sine, cosine. Okay, so we have C and S, and they just come from the original angle, which was theta. Now, let's take 3 other vectors, A, B, and D, which are an orthonormal basis. So there are 3 vectors. A is the x-axis. A represents x, B represents z, and D represents. Oh no, sorry. B represents y, and D represents z. Okay, right? 3 vectors. They are not 1, 0, 0, 0, 1, 0, and 0, 0, 1. Of course, they're just 3 vectors perpendicular to each other, which we call A, B, and D. All right, with a catch. D is the axis around which we want the rotation to happen. Alright? So, first we had a rotation around Y. Now we want to do some magic on R0 and get a new rotation matrix which rotates by theta around the axis D. And no more around 0, 0, 1. Okay? Is it clear what we want to do? Alright, so what happens is that if this is what we want to do, then R1 is the new matrix, and we know that R1 multiplied by A, B, and D, put as the columns of a certain matrix, are equal to A, B, and D put as the column of the same matrix, which we call P, multiplied by R0. Now this is a well-known fact from algebra. This is how you change a basis in a matrix. So what we're doing is simply saying you had matrix R0, and in R0, x is 1, 0, 0, y is 0, 1, 0, and z is 0, 0, 1. And we're saying, okay, give me a new rotational matrix, R1, such that x becomes A, b becomes, y becomes b, and z becomes d. So we're changing the frame of reference of R0 into A, B, and D. And the result, so you know that R1 times P is equal to P times R0. So just take this as a fact from above. Okay? And yes, we can. We know that these vectors are perpendicular to each other. So P is a rotation matrix because when the columns are perpendicular to each other and normalized, then we have a rotation matrix. So we can invert it by transposing it. So if we multiply R1 times P by P to the minus 1, and we do the same on this side, we get. I'm gonna write this. Okay, so we have R1 multiplied by P is equal to P multiplied by R0. We multiply both sides by P minus 1, so we get R1 P minus 1 is equal to P R0 P minus 1. This one becomes 1, the identity, alright? So what happens is that R1 is equal to P R0 P transpose, because P transpose is equal to P to the minus 1, because P is a rotation matrix. Alright? This is already an awesome step, because we have derived R1, and R1 is a rotation matrix around an arbitrary axis D of an angle theta. So this is already something that carries. So we have the angle D, the axis D, and the angle theta. Because D is now the new Z. So if R0 rotated everything around Z, the Z-axis, in R1, the Z-axis is D. So R1 rotates stuff around the D angle, around the D axis. Come on, seriously, this is already awesome. So none of this is particularly mystical. This is a beautiful thing. Okay, so if you do some algebra, you can actually rewrite, because we know what's in R0 and we know what's in P. We know these matrices exactly. So P is ABD. P transpose is something else, and R0 is this one. So we know that R1 is equal to C multiplied by these, which are vector by which are matrix multiplication. So these are matrices. These are not numbers. This is not a dot product. Rows multiplied by columns. So if you take a vector multiplied by its transpose, then you get a 3 by 3 matrix with all the possible pair combinations in all the elements. So 3 by 3 matrix, other 3 by 3 matrix, and so on. So we have these values here, and this is the rotation matrix that we want, derived from d and theta. But unfortunately, we're tracking a and b, which are two vectors which are perpendicular to d and perpendicular to each other, but we care absolutely nothing about them. Why not? Because we're rotating around the axis, right? And imagine I'm the d-axis, alright? And this is A and this is B, okay? Now, if I want a transformation that rotates stuff around the d-axis, whether A and B are like this or A and B are like this, it doesn't matter, because this matrix is still going to rotate around the d-axis, which is me, so the matrix is still going to rotate around my vertical direction. So A and B are simply ways to specify perpendicular directions to D in the matrix, but no more. And so we have found the points of redundancy in the matrix. So we know that A and B can be anything. That is why they are redundant, because they carry no information. They are just a necessity to build a matrix. So we compute, well, because, okay, so what we do now is we compute these two quantities, d cross v, where v is a random, an arbitrary vector, whatever, and d cross v, again. And what happens is that, well, we do the transformation, we know that v can project it on the 3 axes. So what happens is that we can express these relationships with a bit of algebraic steps, which you absolutely don't care about, as a transformation by the d big matrix and by the d big matrix squared. The d big matrix is only derived from the d vector. This is very important, because what we're saying is that there's a relationship between the d-axis and v which seems to pass through a, b and d, but which in reality only ends up being something that has to do with d. So we're building a relationship, an understanding of the relationship between the a and b vectors and the d vector. Because now we know that a and b plus d crossed by d itself have to result in something like this. And we do the same again. So what happens is that now, basically, we derive the relationship between d and v, and indeed, a and b, the a and b vectors. So now we know that d is equal to this matrix here, and d squared is equal to this other matrix here. We combine those, these are just a bunch of steps, but ultimately what happens is that we can derive that the original matrix, R1, this is our rotation matrix. This is the matrix that rotates around an axis of an angle. And this matrix is equal to I plus the sine of theta multiplied by d plus 1 minus c, the cosine of theta multiplied by d squared. But we knew how to derive d and d squared just from d. So now we have built a rotation matrix only from the d-axis and the sine and the cosine of the angle. So we have removed the necessity of a and b, because we could pick any a and b that we wanted, so we find a way to express a and b, which is the d matrix, in terms of the d vector. Alright, so we can even rotate a vector. So if we take R1 multiplied by V, which is a matrix transformation, we know that R1 is equal to the sum of 3 matrices, but we also know that multiply a vector V by the D big matrix is equal to doing its cross product with D. And multiplying D squared by V is equal to doing the cross product twice. So we have a rotation matrix, but we don't need to build a matrix. We just do the vector that we want to rotate plus the sine of D crossed by V plus 1 minus the sine of theta multiplied by D cross V. This is a quaternion. The quaternion is the pair d theta, and if you imagine, computationally you have d and you have theta. So you have d and you can compute the cosine of theta and the sine of theta. And you want to rotate a vector by d and by the quaternion, so this is what you do. This is exactly the steps you take to transform a vector by the rotation expressed by a direction and an angle. And the quaternion simply is a way to put angle and vector in a quadruple, which you then use like this. Any way to represent d and theta together could be fine. So in principle, you could just have 4 values: dx, dy, dz, and theta. But a particularly convenient one is the cosine of the angle divided by 2 multiplied by the sine of the angle divided by 2 multiplied by d. This is just a number. This is the cosine of half of the rotation angle, whereas this is the sine of half the rotation angle multiplied by the rotation axis. These are 4 values. The reason we pick this representation is because of mathematical interest, because normalization of this vector here gives you a quaternion that represents a correct rotation. So normalization makes sense on this representation, whereas normalization wouldn't make sense if you had theta followed by d, because if you have a very big angle of rotation, then you reduce the value of the axis, which is obviously wrong. So this is what you store into, this is what you find into a quaternion. This is exactly what you find in a quaternion. Alright, so at this point, imagine, oh come on, is everyone lost and desperate at this point?
Well, it is 1 hour and 20 minutes in.
Yes, it is 1 hour and 20 minutes in, and it is quaternions after differential equation, so I can see this.
Just getting a headache,
But
that's all.
Can you see 2 very important facts that come from this lecture, from this particular set of axes? The first one is that you know how to imagine you have a buggy or lacking, or you need for some obscure reason, because you are the first developer going into the PlayStation 17, okay? And oops, there's no linear algebra matrices, the linear algebra library yet, okay? So, one thing you will need is a way to deal with rotations. Rotations around an axis and an angle. How do you build it? Last line. This is a very clear recipe. You build P, 3 vectors, and then you build R0, which is a super simple matrix that you can build. These are just numbers, and there you go. Then you have a rotation around an arbitrary axis and of an arbitrary angle. Or you need to store a quaternion, and you need to know that you need to build the matrix that corresponds to a quaternion. This is the matrix that corresponds to a quaternion. Very last line. Exactly. So the function convert quaternion to matrix does exactly this. And if you need to transform a vector by a quaternion, this is exactly how you do it. So when you have quaternion by vector, transform vector by quaternion, this is exactly what you have to turn into code. Come on, sum, cross, multiply, cross, cross. This shouldn't be that hard to implement. And finally, this is how you build a quaternion. So if you have a quaternion, this is how you build it. Yes?
I don't follow anything about quaternions yet. So,
Yes, probably because they're very hard.
yeah.
It takes approximately, in the competitions I made, it's at least 5 to 9 hours of personal study to get into this. So yeah, indeed. We've done 1 hour, so you're 8 hours to go. Okay, so where does all this go? Well, we know how to compute r dot from R and W. We have done it here. But if we represent rotations with quaternions, then we'll need to compute the time derivative of the quaternion. Now, do not worry, I'm not going to do this to you guys. But this is how you do it actually. These are just Okay, so is it clear? Do not, when you see something like this on my slides, usually you don't need to study. Go to the last line. The last line is actually here, but I usually put it also on the next slide. Alright? If you ever wonder for completeness where it comes from, there. Okay, you don't need to study this, so don't. Alright? Okay, so the most important thing is that when you have the angular velocity, which is 3 values, it's just a vector, you build a quaternion where the first component is 0, and the second, third, and fourth components are wx, wy, and wz, omega x, omega y, and omega z. multiply by 1/2 and multiply by the original quaternion. Okay? This is the derivative of the quaternion. Now, you'll wonder, well, is there some relationship? So why does the quaternion happen? If you see here, when we compute q dot, r dot, we have the angular velocity and we have t and v, which are the rotation metrics, the original rotation metrics. And here, if you look closely, we have w and we have q, which is the quaternion, which is the rotation. So the derivative of the rotation always depends on the angular velocity, but also on the current rotation. And, well, can you guess what happens? So this becomes, r becomes a quaternion. So this is quaternion. And it's q. Then everything else, no change whatsoever. Now, this one gets thrown away. We compute j to the minus 1, of course, because we are going to need it. So, we compute. Oh, and no orthonormalization either. So, we compute r, which is from the matrix from quaternion, from the quaternion q. And you'll say, why do we need r? This is just a temporary variable. It's not part of the state. Well, we need r to compute j to the minus 1, which is absolutely needed. Then we compute w. Oh, yes. Then we compute j to the minus 1, which is equal to r times j body to the minus 1 multiplied by the transpose of r. Then we compute omega, because remember, we're tracking the angular momentum, so we need the angular velocity, and this is j to the minus 1 multiplied by L. Then q is incremented by 1/2 the quaternion, where the first component is 0 and the remaining components are w, multiplied by q itself. And then q is equal to, let's call this q hat. Normalize q hat. Alright?
Is the plus is correct?
Yes, plus is correct.
Because you're doing plus equal with the q hat.
Oh, sorry. Yes. Yes. Yes, you're right.
That looked a little bit
Of
silly.
course. So this is multiplied by delta time, and it's set into q.
Okay.
Of course. Yes. And finally, you normalize. That's the derivative. That's plus q. Yes. This is right. And then you normalize. Now the normalization of a quaternion, first of all, is much faster than the Gram-Schmidt orthonormalization that we have seen for matrices. But even more importantly, you don't need to do this every frame. You can do this every 10 frames, 50 frames, because the quaternion drifts very little. So the error that you get with the quaternion is far less than you get with matrices. So you can actually do the normalization process less than you did for the quaternion, than you did for the matrices. So the quaternion is a more precise representation of a matrix. Oh, yes, absolutely. So at the end of these slides, you get some description of how to implement a rigid body in kind of C. Now, because there may be errors here, I can obviously make mistakes. The whiteboard always compiles and runs correctly. So, yes, check this. Come on, this is a big overlap with the rest of with what I've just explained. And this is an example of how you would compute Runge-Kutta 4 on a state of such a rigid body, which is significantly longer code. Now you can see all of the come on, these are just K1, K2, K3, K4. You have to compute all of them, and computing K1 means doing this. Computing K2 means doing this again with other input values. Computing K3, so you see, this is K1, this is K2, this is K3, this is K4, and this here puts puts all the values together. All right, but the structure is this one. The structure is simple, and it's simple is a big word for it, but the structure should be clear enough. All right, shall we take a break?
Yes.
And break on this.
Moet ik hem gewoon zo op pauze zetten? Hey Bram, moet
I'd like to say
ik
this
hem
was
gewoon
the
op een rode knop
toughest lecture.
drukken om op pauze te zetten?
Ja, die is zeker right. En dan
Yes, yes. That was the objective.
Oké.
I mean, yeah. No, this is fine. We are kind of happy when stuff doesn't break down. Whereas, can you see it?
That's yeah.
All right. So, and this is because you see the can you see the box with the crying eyes? There it is, and it's really breaking down. All right. And this is the problem with the Euler integrator. This is the Euler integrator, the error of the Euler integrator. So if you really want to visualize what it means, yes?
Are you also normalizing the matrix?
No, I'm not, of course, to make a difference. Yeah, but do you realize this is after 30 seconds, 10 seconds of gameplay, so this is something that you really need to do. And the normalization is super expensive. Oh, yeah, now it's getting cute, so now it's very low.
Harder to see as well.
Try to use green the next time.
Yeah.
Oh, yes. that is lovely. Does anyone have a cube mesh that they want to share? Alright.
Sure.
Okay. So, at this point, oh, by the way, my implementation of the assignments is online. You can access it. The URL is described on Netsco. So go and download them if you want to see a reference.
But they are in F#.
Yes, they are not in C++.
Yay.
Still using.
They're neither
F#.
no, they're neither in C#. I decided to go. Yeah, F# is my favorite language. So
It's
yeah, just
Weird.
check it out. It's a weird mathematical language. That's the easiest way to describe
Is
it.
it something like Haskell or something?
Yes, exactly. It's
something like that,
it was
yeah.
developed across the whole as Haskell.
Right.
So it's absolutely wonderful if you need to do mathematics.
With Haskell, you can basically rewrite a loss of math in it, right? You can just
Yes, absolutely.
you can just
Yeah, but in this case we're staying
you can
in
make
the
a
boundary.
program that's like 2 + 2 = 0. It's like okay.
No, but okay, all right. We will discuss about that. No, basically, functional programming languages like Haskell and F# are languages where mathematical formulas are at the core of computation. So what you'll see are definitions which are very much in line with what you see in the slides, which is the reason why I use it with great pleasure. Okay. Oh, right. This is an easy set of slides. This is the only one, and it only lasts for 8 slides, which is approximately 10 minutes. Then we do something else, more fun. Okay, so you know that our objective is basically to apply Newton's law of motion, which is this, to linear and rotational movement. This is assignment 1, and yes, it is easy from the standpoint of physics. And then we have to do the collision detection, which is ensure that moving objects do not interpenetrate. And that is hard. Now, alright, about easy and hard when it comes to physics, there's a bit of a confession that I need to make, and I'm making this in front of a camera. Can you pause that thing for a moment?
Yep.
Okay, so a physics engine does have its own update and its own loop, basically, where besides the rotational and linear movements, we need to find pairs of objects touching. We have to find the time of contact. We have to find the points of contact between the objects, and then we have to apply external forces to the objects to counterbalance their current forces and how much they're breaking the constraints of the system. So basically, if two objects get too close, we apply a force that ensures that before this frame is over, they will be pushed out of contact. Alright? So you have two objects, they interpenetrate, and now you know that the delta time is 0.01, for example, and then you apply a force that in 0.01 seconds pushes them apart. Okay? This is roughly the way it works. No, this is exactly the way it works. How do we find the pairs of colliding objects? Well, we have a broad phase of collision detection, which with axis line bounding boxes. That is actually an easy topic. Yes, that is truly, honest to God, an easy topic. Then you do the medium phase collision detection. Oh, wait a second. Do you know what an axis line bounding box is? Who knows? Oh, alright. Well, an axis line bounding box is a box where the axes are where the directions of the box are aligned x and y axis. Alright? This is an axis-aligned bounding box. This is not. Why? Because its sides are not aligned with the axis. Alright? Okay. And is this a... if you have to make sure that whatever rotation or movement of the object, it remains inside an axis-aligned bounding box. Is the axis-aligned bounding box a good approximation of an object? Unless it's a box nailed to the ground with this shape. No, imagine you have a character and the box has to be very big because the character may rotate in lots of directions. So the box is much bigger. But the fact that the box is aligned with it, yes?
Can you scale the box dynamically depending on the rotation of the character?
Then it's an oriented bounding box. Oh, what you mean? Oh, yes, of course. You can do something, yes, that is prettier. You can track the original axis-line bounding box. You rotate its vertices, and then you recompute the axis-line bounding box around the rotated vertices. Yes, of course.
You can also calculate it from the OBB, right?
Which is this is exactly calculating it from the OBB, because first you have the original bounding box.
All right.
Then you rotate that, then you have the OBB, and then you do the axis-line bounding box around the OBB. All right. So, but in line of principle, well, especially, what's the worst case? Leaning. So, if this was your object, then here you get a rather big axis-line bounding box, because this is the OBB, this is the oriented bounding box, and the axis-line bounding box is going to be this one, okay? Which is still very big, right? And so the answer is no, this is not a good approximation of an object, but why do we care about it?
It's much faster.
Because it's fast, incredibly fast, especially if you have a bunch of objects and you want to find all the pairs of collisions between all the the axis-line bounding boxes at the same time. There's amazingly fast algorithms that do not even require you to track a tree or some other complicated culling structure. So you just have a list of boxes, and that's it. A sorted list of boxes which is sorted with insertion sort. That algorithm is amazing. So we'll see that. Now you know that, okay, these two boxes are indeed colliding. Here you have, I don't know, something else, a bullet.
More like a rocket.
Alright,
It's a big bullet.
alright, it's a rocket. And okay, these boxes are colliding, right? But the objects are not colliding. So yes, we'll have to wait probably another frame until the gratifying gory explosion. But how do we determine that they're not colliding? Well, first of all, we have the oriented bounding boxes. In our case here, the oriented bounding box is this. And we could do another step of collision detection with the oriented bounding boxes, or we could approximate the object as a series of bounding spheres, and we could do the collision detection with a series of bounding spheres, and so on. So this is what we call the medium phase of collision detection. But then, at some point, the rubber hits the road, and we really need to know the precise collision detection. We really need to know if the two convex meshes are colliding with each other. Alright? And that is the narrow phase collision detection, which finds not only the exact time of collision, but also the exact points of, well, not exact, but some interesting points of contact. And you need the precise response, because if you need to do collision response, then you need to know, you don't just need to know that the bounding box of the marker is touching the bounding box of the table, even if it's an axis, even if it's an oriented bounding box, so it's precise enough. You now need to know exactly which vertices, which points of the surface are touching, or in this case, because you can imagine the way things fall changes very much with the exact point and direction of collision. All right. The last step is indeed the most important and the hardest one. We'll start tackling that in the last part of the lecture. Then we have to do the collision response, which is between pairs of objects which are colliding. So at first one may say, alright, let's use some formula, like, I don't know, some Haberle formula or whatever, between pairs of objects, just to apply the laws, or just to apply the law of conservation of momentum across the direction of collision. And that could work if all you're doing is bouncing balls, and if all you have are two balls. But imagine you have multiple objects collide, or first of all, imagine you have lots of objects, hundreds of objects, all touching each other in complex manner. So you have an object that's touching three more, a stack of objects, whatever. The first response of just resolving collision between pairs of colliding objects doesn't work, because during a frame you'll probably get in a case, and this is for all practical purposes unavoidable. You will get a case like this: a bit of interpenetration here, and a bit of interpenetration here. All right? So you say, okay, but this is easy. So you solve the collision between, say, the first two, 1 and 2, and what happens is that now you get that, okay, 1 is free, 2 is moved. Oops. All right, but we haven't worked on 2 and 3 yet, right? So we work on 2 and 3. Yes, of course. So now what happens is that, well, we free 3, but now 2 goes back in there, because you're pushing everything away from the collision. Then this is the third drawing is a bit exaggerated. So one way to solve this would be to, yes, you keep doing this until you don't have any collisions left. You can. It works. But yeah, this is a way to do this. Or there's far more interesting ways to, this for example wouldn't work at all if the objects were stacked. So if you have a stack of boxes and you want them to remain stacked.
Excuse me.
Questions? Oh, alright.
Sneezed.
Oh, okay. So if you have a stack of boxes and you keep moving them away from each other, then they are going to wobble and fall very quickly. So this solution is decent. I mean, this is the easiest of the. Okay, I don't want to really say right solution, but acceptable solutions. But there's much better ones that work far better. And it's not very fast as well, because you may need to do a lot of pairwise collision responses, because you may have lots of objects, and if you move them one after the other, but you cause new collisions, so the process may terminate after a lot of steps. Alright, so the collision response will balance all the contact constraints, but the kind of method that we will study doesn't just handle collision response, but it also handles constraints such as distance constraints. So 2 points in 2 objects have to remain at a fixed point, or friction constraints, like an object is sliding on top of another, or joint constraints. So basically, the collision response technique that works best is also capable of doing everything together with inverse kinematics. So doing collision response right gives you a power which is amazing and which goes way beyond the simple power of collision response itself. So this is something which has a lot of value, which goes into all areas of physics and kinematics. Alright, so roughly this is the general layout of a physics engine. So first of all, you'll initialize, and when you initialize, well, you'll set up the bounding boxes, the bounding volumes, bounding spheres, oriented bounding boxes, binary space partitioning trees or Gauss maps for making collision detection quicker, the inertia tensors, everything that you need to start up your bodies correctly. Then in a tick, you'll update the axis line bounding boxes, for example, like we described before. You find the axis line bounding box intersections. You refine these intersections with the bounding volume tests, like bounding spheres, oriented bounding boxes, whatever. You may also not do this, if it makes sense. I mean, this is a matter of profiling at some point. This is a step that you may want to do if you get a lot of spurious false positives from the axis line bounding box intersection, so you have to reduce them. But the last step that you must do is the separating axis collision detection, which is the precise method, which is very heavy. So obviously, if you get too many false positives, then it may be a very good idea to cull some of those false positives away. This gives us all the collision points between the bodies. You resolve all the constraints given by the collision points, friction, distance, whatever else you want to support with this method. And then you know the forces that you need to apply to make sure that objects do not interpenetrate. And finally, you apply the kinematic step. And the force and the torque of the kinematic step come from input, but also come from the collision response system. So the collision response system incorporates all the forces and the torques that need to be applied in this frame to the body update. Alright? Good. Okay, so this is... Yes. So, I almost forgot. The actual assignment 1 starts now. So yes, you have 1 week more. And this means that before the end of next week, so before Friday midnight of next week, you have to send in the first assignment. Now the first assignment contains rotation matrices, quaternions, normalized quaternions, and what was the last one? External applications of forces and torques, which you handle with input, and so on. So roughly what I showed before is, if it's still on. Yeah, it's coming. So this little thing here is a valid application, is a valid solution of the first assignment.
But in the wrong language.
In the wrong language. No, you can submit it in F# and Haskell. I will accept 2 more languages, which are F# and Haskell. But not, you can't send me my own implementation, of course. Alright, so I can apply a torque. This is a torque. As you see, there's no friction, so when it starts rotating, it keeps rotating. I'm pressing the opposite button. One thing that's very important, it has to feel very smooth. When physics is implemented correctly, the feedback you'll get is of very smooth movement. So when I start pressing, I get the feeling that it doesn't start right away. It's like pushing. It's really the feeling of pushing something. Alright, and then there's... Oh, wait a second. No, stop. Yep, okay. And then I'm applying a force. No, wait a second. Was it enter? Is this the right? Oh no, this is not the right one. Or is it? Oh well. Oh yes, I'm not applying any force. So
Use the force.
alright. And the other one as well. Now I'm touching code at runtime during a lecture, so this is, yeah.
It's recorded. Your professionalism is now forever.
Okay, ooh, yeah, this is fortunate. Okay. So this is the application of, okay, I'm applying a gigantic force, so this is obviously not a good idea. What's happening is that I'm applying a force to a corner. So you see that the object starts rotating and moving, as if you hit it on a corner, okay? Now when the object starts rotating and I keep pressing the space button, I keep applying a force that forces to spin like crazy, so that's what you saw before. Yes?
Are corners good enough, or do you need to be able to apply a force on any point on the tube?
Like this, hard-coded, that's fine. So you can have it hard-coded. In this case, when I press space, I just apply it to one of the extreme points, right? To the size divided by half, which is one of the positive extreme point. Alright. So this would be a valid assignment 1. Just so you know. If you can turn it into a spaceship, then it's cuter, but I mean, it is exactly the same principle. Alright. Alright, so
Are you doing
collision.
all the lectures in one lecture? Or?
Yes, I call them lectures. Well, technically lecture means reading. So these are slides that I read to you guys. It doesn't mean lessons.
Oh my god, we're already at the end of the block.
We're already done.
Okay, so let's take 5 more minutes of break before we delve into collision detection.
Yay.
Before we resume, I wanted to share the second and third assignments, how they should look like. Now this is collision detection. You can see that there's 2 boxes, and the tiny boxes represent the collision points. It's not very easy to visualize them, but basically whenever an edge crosses a face, that is a collision point. Alright? You can't really do it for every pair of edges and faces. First of all, because it's crazy expensive, and second, because you really need to find 2 interesting faces. So we actually just consider, you see that now we're considering this face here and that face there. Oh no, wait a second, this face here and the side face of the cube.
You maybe hit the
And now
lights.
they're not colliding anymore, so the box has exited from Yeah, now I'll push it back in. Yes. And it's coming. You see the points that come into place. All right. You see the points of collision. This is what the second assignment should roughly look like.
It's not countering it. I guess.
Sorry?
It's not countering it, otherwise it would
No,
bounce
no, no.
off,
This
right?
is collision
Yeah, detection.
detection.
Yeah, okay.
Yes, absolutely. And now for collision response, I'm going to show something which is the very same kind of collision response as you get for collisions, but not for collisions. One of the things you can do with collision response, and this I probably said this multiple times already, but it's still very interesting, is that with a good collision response system, you can treat any constraints of the system as collision constraints and generate the forces that counterbalance collisions. For example, you have two objects, and in this case there's two objects which are connected by an unbreakable segment in two positions. And these two positions have to be at a fixed distance. So the system starts with the constraint broken, and it restores the constraint and then maintains the objects. So the points of contact... Yeah, come on.
Yeah, that helps.
The points of contact are in the middle, top of... Yeah, you see, these are the points of contact, okay? And the system is pushing them away because they're violating a constraint. You can only push them away slowly, and it shouldn't really happen. So the collision, this is an extreme case where a constraint is broken very much. And you see also that what's happening is that the boxes are pushed away along the direction of the constraint that's broken, and so they're also rotating because nothing stops them from rotating in the other direction. And there they are. And then the system stops, right? This is resolved as one of the multiple constraints of the collision response system. And you can even... Oh, wait a second. Let's hope this still works. I'm always slightly scared. Okay, so I move one of the boxes, and do you see the constraint that's maintained? You see, so the only thing I'm telling to the collision detection system is make sure that those points never get too close. Oh, and now they're rotating into each other, but there's no collision response at the moment. But what really is going to happen is that the constraints are trying to remain...
Explosion!
And then it explodes, unfortunately. All right, but so this is roughly this is a vision of the steps ahead. Wait a second.
Oh, Windows. Always so fun.
It did say something about optimal resolution, but
Yeah.
I think it changed the resolution.
Yeah. All right. Once again.
Windows being helpful.
yes.
Yeah, because running the video card in game mode breaks the presentation mode.
Oh my god.
Of course, that makes perfect sense.
All right. So we will now introduce collision detection. Point of collision detection is we're talking about the narrow phase of collision detection. So the one where we really find points of collision. We'll talk about convex polyhedra, which are what we work with. We'll talk about the separating axis test, which is at the core of most collision detection systems. And there's two competing techniques, which are separating axis test, or SAT, and let's not kill students, please. Yeah. And then there's the GJK method, which, well, it's rather powerful, but very convoluted other method. So we are using SAT because it works, because it's easier to do continuous collision detection, so continuous collision detection between objects that are moving. But this is not the only method. There is a big one that's competing with it. The answer of which one is better is absolutely unknown at the moment. There's engines using one, there's engines using the other, and they are very good methods. So just be aware that I'm showing you just one method over two very important ones. Okay, then we'll talk about how to improve separating axis test for moving objects, which is one of the biggest advantages. So if you have an object like a car moving very, very fast and there is a wall, you can actually predict that there is going to be a collision. Even if the car is running at 350 kilometers per hour, which in most cases would mean that you would just skip the wall in one frame, what's going to happen is that you'll find out that the system is going to tell you, no, even though you're not colliding at the beginning and you're not colliding at the end, there is still going to be a collision after 0.005 seconds. Alright? And finally, we'll delve a bit into the black magic of finding a contact manifold, and there is no proper answer to the question of how do you find the collision points. There's a lot of art in it. You can track lots of points, really huge. You have a huge amount of options possible, and you just have to decide of all these options, which are all geometrical intersections, which are of interest to your application and which are not, to fit to the collision response system. Alright, so the question then becomes, for every pair of rigid bodies, do they intersect? First thing we'll worry about, when will they intersect during the frame, if they're moving, and exactly where is the intersection so that we can do the collision response over the intersection. We need to have good precision. If we have a good collision response system as the one we will be using, we can accept and tolerate small interpenetrations. So precision doesn't have to be exactly perfect. Performance is the biggest problem, because collision detection is very intensive computationally. Even oriented bounding boxes require upwards of 150 individual separation tests, which is a hell of a lot. Imagine for things which are even more complex. So performance is at the core of our worries. Alright, and then we'll do the response, of course, which ensures that at all points of contact that we found, the relative velocity projected along the normal of collision must be non-negative, meaning that when you have a contact, the response of the collision response system has to be that along the direction of contact, the new velocities have to be in opposite directions. So every point of pair of points of contact has to be moving away from each other when the collision response system is done with them. So no pair of bodies which are already in contact gets closer, because otherwise this would mean that they are in contact and they're going even more into each other, which is obviously the wrong answer. Oh yes, okay. So about the concept of relative velocity, now imagine someone has done a very bad job of managing the schedule of trains. So we are presumably in Italy for something like this to happen.
No, it was in Spain, right?
There was a bomb, right?
Yeah.
For the Netherlands, it would just be somebody ignoring a red sign. So nobody's perfect.
Now, if this is the situation, and we have two velocities, VA and VB, one of the first, this is a simplification, but not an approximation. We will deal with these objects as if just one of them is moving, and this is the concept of relative velocity, which I'll give for granted in the rest of the lecture. So we'll just try to get familiar with this. Now, we could get this situation, or we could get from the collision detection and response system an exactly identical situation, as if we were object A were moving much faster, right? What speed does A need to have so that this situation is exactly the same as this one? Yeah?
VA plus VB.
Almost.
Oh, yeah.
VA minus VB, right? Okay. And this works whatever direction you have. So if this is the direction, then this is fine. It's as if VA would be a bit shorter and to the bottom, and so on. Okay? So only one of the objects, the first one, is moving, the other one is always standing still. This doesn't make a gigantic difference, but it helps a bit. Alright. So, well, yeah, this we've said multiple times. Alright, hopefully, if you manage to get the third assignment done perfectly, you will be able to arrive to the point of stacking a bunch of boxes together. Most likely you won't. This is very, very, very hard to do, so just accept that it's very hard. I'm not even sure if I'm going to make it myself. So, but the technique you're using, because you need to cache the contact points between frames, and that is the hardest part, one of the hardest parts. But anyway, the collision response system that we will be finding is going to be able to do really awesome stuff. And this is awesome. In collision detection, this is considered absolutely awesome. Are you aware of this? So, if an engine says it does stacking in a stable manner, yes, go for it. Okay, stacking, awesome. Okay, what do we work with for collision detection? Now we'll get into a bit of technical details. We'll only work with convex polyhedra, so we'll only work with convex stuff. So, is this convex?
No.
No. Is this convex?
Yes.
Yes.
Yes. Is this convex?
Yes.
Yes.
Is this convex?
Yes.
Yes.
Is this convex?
Yes.
Yes.
Is this convex?
No.
No.
Very good. So, okay, looks like the recognition rate is high enough. This is not convex because there exists a pair of points, which is what's on the second line there, such that their interpolation is outside the object at some point, right? If the interpolation of the objects can fall of 2 points inside the object can fall outside the object, then the object is not convex. Whereas here, wherever you pick 2 points, every point between them will be inside the object. No way to escape the object from inside. Okay? Alright. Why do we need this? Well, because you can easily imagine collision detection between these two objects like this. Yeah. It's an amazing pain in the effort of writing code. So, yes.
You could chunk it in small boxes.
Yes, exactly. That is precisely what we do. So if you really have those kind of objects, then there is a very easy solution, which is you cut the object into a bunch of convex pieces. And they can be very precise. So imagine I'm actually drawing exactly where I have drawn before. Yeah, in this case you may actually need to tessellate a lot, but in general, sorry? But in general, the idea is that you split it. So a human body, for example, you can easily approximate with a bunch of convex meshes. Okay, they can also intersect with each other. It doesn't matter. It won't do any damage. Okay. Oh, which indeed was the third line there. Okay. So these are examples of convex polyhedra. Now, how do we find if two objects are colliding or not? Now, actually, this first part is surprisingly simple and surprisingly elegant. We use a method which is called indeed the separating axis test, which looks for an axis that separates the body. Or in 3D, we look for a plane that separates the bodies. Now, mind you, this is not exactly what we do. We will always work with axes. That is why the method is called separating axis. And this method, nicely enough, works exactly the same in 2D and 3D. So the same source almost works from 2D to 3D, which is usually not the case. So this is also a very big plus. Now, the axis that we're looking for is not really the one that separates. It's an axis along which the projections are separated. So, this is the reason why it's called separating axis. The separating axis is an axis along which projection there is a separation of the objects. So, you have these objects, and let's take this axis here. Alright, is this a separating axis? Why not? Let's draw the projections. This is the first projection, and this one is the second projection. Are these projections separated? No. Alright. Let's go for this axis here.
No.
No. Let's go for this axis here. Is this a separating axis?
Yes.
Yes, it is. Now, of course, if you're in 2D, then you can also say, alright, if I take the separation interval, and I take a line that's perpendicular to it, and I have also found an axis that actually separates. Or, if I'm in 3D, I can turn this into a plane, and I can find the plane that's separating. But usually that's irrelevant information. What really matters is the axis of separation. Okay? This is the axis, the separating axis. Alright, so the idea of the method is that for every for our polytopes C0 and C1, we project them over some direction D. D is the direction of the separating axis, and we find the minimum projection, we find the maximum projection, and we call them lambda min and lambda max, and we see if lambda min of the object 0 is greater than lambda max of the object 1, or if lambda min of object 1 is greater than lambda max of object 0. I will stay on this slide. Let me see what's after. Nah, we'll stay on that one for a bit. So, let's give a name to these things. So we have the two objects, and we have a direction D. Okay? And actually, let's say that the separating axis always passes, a separating axis always passes along the across the origin. And you'll say, okay, but aren't we, so all the separating axes that we consider pass through the origin. Doesn't this make you wonder if we're not excluding important separating axes? Why not?
Because in essence, every plane, no matter what position it would be at, would be just be perpendicular. It's an infinite line, so...
Yeah, so the translation of, so let's consider what we're excluding basically is the notion, the point is the perpendicularity between of the projection. So if we take this alternate axis here, the projections are going to be
exactly the same.
Exactly the same. Why? Because the two axes are
Perpendicular.
Are parallel to each other. Right? So we just don't care about this one. We just care about the ones that pass through the origin. So the translation of a separating axis remains a separating axis. So we just go for the separating axis that cross the origin. So now, what do we call this vector here, this point here? We call it lambda min. And if this was object 0, this is lambda min of 0. And we call this lambda max of 0. And this is object 1, so this is lambda min of 1. And this is lambda max of 1. Okay? When do we get... Oh, and lambda refers to the distance from the origin along the axis d. Alright? So this is lambda 1, is lambda min 0. This is lambda max 0. This is lambda min 1. And finally, this is lambda max 1. Okay? Are you still following? Okay, now, when do we not have a collision? Yep.
When lambda max 0 is smaller than lambda min 1.
Of course, right? Unfortunately though, the objects may be in the opposite order. So you may have 1 and 0. Like this, and you don't know before. So, you also have to check the opposite case. So if lambda max of 1 is smaller than lambda min of 0. Right? If you can find a direction D, project the two bodies along the axis, and you can find that lambda min of 0 is smaller than lambda max of 0 is smaller than lambda min of 1, or that lambda max of 1 is smaller than lambda min of 0, then you don't have a collision. You are certain that there is no collision. If you can find an axis such that the projections are not separated, you don't know anything. So you only look for an axis that separates. Remember that an axis that doesn't separate, like this one, you can always find it. Right? It's the axis that kind of tries to put the objects one behind the other. Alright? So you always have axes that do not separate. But what you're really looking for is just one that separates. If you can't find any axis that separates, then you have a collision. Go.
Yeah, that was...
Oh, yeah, okay. Indeed. So this one we've seen already. How do we compute the projection? Now, the projection for every point, so you do know that this object is made of points. It has points, whether it's triangles or other shapes. It's got a bunch of points. And for every one of those points, you project it along D. How do you do a projection? How do you compute lambda min? So, the projection of a vertex, say a vertex x, did I use x? Yeah, a random vertex x in a body, okay? How do we find its projection here? X dot product D. Remember that the dot product gives you a projection of one vertex along a line, okay? And indeed, if you really want to see why, remember that when you do the dot product, You take x is this vector here, d is this other one, and you are projecting a perpendicular line. And you are getting the result of the projection. Yes?
And the x must be in world space.
X must be in world space, absolutely. That is the first case where we do get world space, absolutely. Yes. So, you do this process for all the x's in the first body. You find the minimum projection and the maximum projection. And you have lambda min and lambda max for that particular body. You do the same for the other one, and you check to see if there is a collision. If there is a collision. Now you can build. Let me see. Oh yeah, of course. Now if. Oh yes, this is important. So if you can test all the axes in some manner, and you find out that there is one that separates, as soon as you find out one that separates, you stop. There is no collision, and you simply say no collision or safe. So now the problem becomes, how many possible x's do we have that we need to test on? Yes, infinite. And can we test an infinite number of x's during a frame? No, we cannot. So, well, we need to find a set of x's which is interesting enough to guarantee that we find the separating axis if there exists one, but which is a set that's as small as possible, and we need absolutely this set to be finite. So first of all, 2 notes. The first one is that if you translate a separating axis like we did here and here, you get the very same separating axis. So if the bodies are separated along this axis, they are going to be separated along any other axis that's parallel to the original one. So this already excludes plenty of possible axes. Also, you can multiply d by a non-zero constant. So d usually, and this is a good idea in general, but you can decide to have d which is not of length 1. What happens is that if d is longer, if d is longer, then the projection is going to look well, actually. So this is the okay. This is the regular d. Okay, d of length 1. So the projection you get is the obvious one. Okay. What if d is longer than 1? What kind of projection do you expect?
Scale.
Scaled. The projection is going to be scaled. So you'll get something like this. And you will, and if you have a separation on the original axis, the separation is still going to be there. It's going to be farther or closer. But it doesn't stop being a separation, because you just multiplied the lambdas by the length of d. Okay? So you shouldn't worry too much about having these that pass through the center, or having these which are or are not of length 1. But of course my advice would be make sure that d is of length 1. Okay. Alright. Oh yes, the scale of separating axes. A bit of art to remember. So here you see the projection on the first axis, d, which is here. And then there is the projection on a scaled axis, half, and translated. And you see that the projection goes smaller. And the lambdas are half what they were here. Okay, so if this lambda was, I don't know, 4, this lambda is going to be 2. Alright? Good. Yes, and this is the translation. So you translate all the x's, but the projection is going to be the very same. And the alphas will be the very same. The lambdas will be the very same. Oh yes. I shouldn't put this on official documents. They're too obvious. Okay, so to apply the method of separating axes, there's some cleanup to do on the bodies. So your bodies should contain the vertices, and the vertices should be, well, in 2D order counterclockwise and with rapid indices. So the nth vertex is actually the first one. The n+1 vertex is actually the first one. You should store the edges ordered counterclockwise. Now the ordering is very important, because if you switch the order, then faces and edges start to point towards the inside of the body. So storing the edges and the faces clockwise or counterclockwise, as long as you are consistent, makes sure that all the normal directions that describe what the face points towards are towards the outside of the object. Alright? Absolutely crucial. Is this clear? Very clear. Who doesn't understand this? Who doesn't find this perfectly clear? Okay, so one very important thing is the normals of the various faces or edges of a body. What are the normals of a face? Where do they point towards?
Outside.
Outside. Very good. Is this a normal?
Yes.
Yes. Is this a normal?
Yes.
Is this a normal?
No.
Oops. How do you compute the normals? Usually through the difference between, well, the normal of a triangle is ABC, is usually the cross product of B minus A crossed by B minus C. Normalized. Right?
True.
The problem is that if you swap B and C, the normal goes from this one to that one. So the order in which you store your vertices actually breaks the way you compute normals. So storing the vertices into the edges and into the faces in a consistent manner is absolutely fundamental, otherwise your normals will point to the inside of the object, and the collision detection system is entirely based on the normals, which presumably should be correct. Okay? Yes.
Does this mean that you have to order the vertices every frame?
No. Please don't.
No.
Oh, interesting question. So what you're wondering is whether a rotation turns your vertices from clockwise to counterclockwise.
No.
Oh,
I just
that's a
mean
pity.
that it should change every time that it either rotates or
So, yes.
moves. But I don't. Then the ordering should be done too, right? Every time the object moves or rotates.
No?
Not better than the clock. Throw on the clock, it still goes the same way.
That is actually a good metaphor. But the idea is that if this some... Oh yes. So, let's say that we have our vertices, okay, here's A and B, they're one on top of each other, we cannot see them, and here's C, right? Now, we rotate the object, so the object is rotated like this. Okay? And yes, now A, B and C are going to be in the opposite order. Actually, if the rotation, this object is almost it's actually quite symmetrical. Nice. A victory for Giuseppe the drawer. So you see, the points are now in the opposite order. Can you see it? And the normal, oh, it's in the opposite direction. Which, oh, is what we want. So yes, you don't need to recompute anything, because if in the first frame the normal points to the outside, then even if you rotate the object, the normal is going to be rotated by the rotation matrix. The normal is pointing now in the opposite direction, but it's always pointing in the same relative outward direction. And the reason for this is actually because in that case, these are not A, B, and C, but they are R multiplied by A, R multiplied by B, and R multiplied by C, right? Because the object is transformed. Right? Okay. So, we do RB minus RA cross RC minus RA normalized. What we can do is we can actually factor out the rotation matrix. So we can actually factor out, so here becomes R of B minus A cross R of c minus a, but we can factor again r of b minus a cross c minus a. And finally, we can bring the normalization inside, because because this is a rotation matrix, and a rotation matrix doesn't change the length of things. So the length of this vector is equal to the length of this vector, because this vector here is being rotated by the matrix. So the final result is r multiplied by b minus a cross c minus a. And what is this? Come on, guys.
The transformed normal.
It's the original. So this one was the original normal, and this is r times n, which is the transformed normal. So when you rotate the object, what's happening is that the normals are rotating with the object itself. And that is exactly right, because the normals have to rotate with the object, otherwise they stop pointing in the right direction. So yes, a very important thing to remember. Care about your directions. Think about this more on paper, because it's impossible to debug. Alright? These are the things that make programmers go crazy, alright? Crazy as in banging the head against the wall in a dark room. Okay. Now, so, let's now find out. So now we have our object, it's neatly sorted. The candidate directions of D are the normals of each polygon in 2D. The normals, because we only have these three possible cases of collision in 2D. We can have an edge against an edge, we can have a vertex against an edge, and we can have a vertex against a vertex, alright? And in all these cases, you can find one, because of the convexity, you can always find that one of the normals is the separating direction. In this case, a normal of any of the faces is fine, because, well, kind of obviously, the normal of this or the normal of this one are both separating directions. And actually they're the same separating direction, but negated. In this case, the normal of this face here is a separating direction. Right? And in this case here, the normal of this face here is a separating direction. Is this clear? Do I have to draw the normal? The normal is here, it goes in this direction here, which is a separating direction. And actually yes. Let's draw this. So, in this case, this is the perpendicular direction. This is the normal of this face here. Alright? And this normal here is a separating direction. So the direction is this one. And here you have the minimum, and here you have the maximum of the other, or the opposite. Actually, this is the minimum and this is the maximum. And they are separated by a tiny amount. Or you can imagine this is a zero separation. So this is the point right before collision happens. Alright? In this case here, this normal, the normal of this face, once again, this axis here, and separation is here, and here, and you can imagine that they're not yet colliding, but almost there, and so the normal is still separating direction. And in this last case here, yes, let's take the normal of this one here, of this face, which is now going to be tilted a bit, so you get a bit of separation once again, alright? That drawing is better as a reference, of course. Alright, so what this means, and this is very important, is that the only candidate separating directions in 2D are...
Normal.
Yes, say again.
Normal.
Yes, the normals of both polygons, both polytopes, right? So you have two of them, and you have to test all the normals against all the vertices of both polytopes, alright? Yes, this is expensive, very expensive. So for every normal of one object, you check all the vertices of both objects. You compare the minimum and the maximum, and this tells you a collision, if there is a collision. Now this already, can you envision how you implement this? For every normal, for every of one body, for every vertex of the first body, you find minimum and maximum. Then you do the same for every vertex of the second body. You see if there is not an overlap, this normal is a separating direction. Great, you don't have a collision. Otherwise, you do have a collision. So this already is a collision detection system. Yeah, come on, this wasn't that hard. Come on, guys, don't do these faces. Seriously.
It's hard.
This is collision. We've done collision detection between objects with triangles and vertices and this kind of stuff. This is not fake collision detection with spheres. This is the real deal. And this is surprisingly clean as a conceptual framework. But we can do something that reduces a little bit the number of checks. So when you pick a normal, you can also take a vertex on the edge that gave you the normal. So every normal comes from an edge, right? So from that edge, you pick one of the vertices. Now what's the projection of that vertex along the normal? Let's take that as the reference. So let's draw two separating objects, and this is the edge, and this is one of the vertices, a random vertex. Right? This is normal. Now, first very important thing, all the vertices on this edge are going to be projected here. Is this clear? So this vertex here is going to end up here. Another vertex that this was a triangle and it was there, it's going to end up here. So we pick just any of the vertices on the edge is going to end up here. Alright? Good. This is our new 0. This is our new origin. Now we have another vertex on the other side. So we just consider this one. We don't consider all the other vertices from the other side. So we have V here. We project V minus P. Alright, so we do D dot V minus P. Or if you want, you can do, well, you can call O as D dot P and do D dot V minus D dot P. This is exactly the same thing. So basically what you're doing is you're seeing what do we want to know. So this would be D dot V. We are interested in this value, right? Let's call it L, the length of the separation, right? What do we want L to be?
But are we finding a collision or?
We want to know if this is a separating axis. So we are looking for non-collisions.
No collision, so then
Yeah.
then it doesn't. It should be positive, right?
Yeah.
Oh, it has to be?
Positive.
It has to be positive. So we need L to be greater or equal than, or okay, let's say when it's equal to 0, then we have a collision. So L has to be greater than 0. Okay? So what we do is we don't check for all the vertices on this side. We just check for all the normals, the faces on this side. We pick just one vertex and we see if the projection relative to that vertex, so this becomes the start. So we're just considering if all the projections fall on this side, on the separating axis, alright? So if all these projections, the projection of these vertices, compared to the projection of this one, are greater than 0, then this is a separating axis. Whereas before we had to project all of these. But we know for a fact that the projection of P over D is lambda max of the object 0. There's not one that's going to be more beyond the edge, because the object is convex. Alright, so now we check for all edges of one body, all the vertices of the other body. Okay, this is still heavy, but at least it's half as heavy as before. And okay, twice as much, that is already a good start. Indeed, so this is the idea. So we set this as the 0, and then we just compare the minimum of all these projections to see if there is a collision. Oh yeah, this is a sample implementation. So you have two convex polygons, C0 and C1, and for every vertex, I0, and for every next vertex, I1, so I1 is always greater than, is always equal to I0 plus 1 modulus the number of vertices. You get the vertex, you get the normal of the face of the vertex, and you see if the other polygon falls entirely on this side of the projection of the vertex and the direction. So this is exactly the code for this description. Just download it and read it up. And you do the same for the other body. So for the other body, you go, you pick a vertex, you pick the normal of its face, and then you see if the other body is entirely on that side. And what we say is we return false as soon as we find a separating axis which tells us that yes, the bodies are separated. So what this thing is doing, it's testing intersection. So it says false if there is no intersection. A very quick question is this faster in detecting collisions or not? So does it take longer to find out that there is a collision, or does it take longer to find out that there is not a collision? Yep.
It takes longer to find out if there is a collision.
Because it has to test everything, and when it's excluded all the separating axes, then it can finally say, yes, there is a collision. Alright? Surprising. But so it is. The idea is that when you get to the point of test intersection, you've done the axis aligned bounding box test, you've done a lot of other things, so you are very sure that yes, there's probably a collision here. So this is actually good news, because it means that if you can exclude it quickly, you've done it already. So these are the objects for which a collision is likely. It's more likely that there is a collision than the opposite. Alright, and to check which side we are in, we check all the vertices of the other polygon against the point P, which is the point of reference, and against the direction D. But yeah, I mean, read this. This is very close to an implementation. This is almost C. Okay, alright. Now, how can we make this faster? There's plenty of ways, but we are not going to see them in the course. That would go from hard to impossible, unfortunately. Unless you want to vote a majority. Who wants to do them?
Like now, or?
Yeah, just kidding. So the point is that you can even find the minimum and the maximum of a projection of an axis by sorting your vertices in by projecting them on a Gauss map. So basically you project them on a surface and you find the minimum and the maximum very, very quickly. So you don't even have to look all the vertices. You find very quickly which one is the smallest projected and which one is the farthest. It is very much like a binary tree. You know, binary tree, it works. It is very same. So basically you sort the vertices across the possible query directions, and yeah, then you find the minimum and the maximum. That is the intuition. And this means that the cost becomes, for every normal here, 2 logarithmic queries. So this is really fast. But yeah, then the code becomes almost unmanageably complex. Okay. Yeah, you can also, though there's another way, another technique. So for every direction, the minimum and the maximum are always the same, right? So if I test the same separating axis, then the minimum and the maximum here will be the very same. What you can do is you can pre-compute, say 100, 1,000 separating directions. When you get a separating direction, you find the closest one that you had pre-computed, you get the minimum and the maximum in constant time. This would be a hash table of the separating directions, alright? This is the fastest method ever. It offloads on the pre-computation. So it offloads on memory most of the computational expense, because then when you're given a direction, you just look up very quickly the closest direction you have, and you give the minimum and the maximum of the projection across that direction. Constant time. So for every normal, constant time. The fastest thing ever. This is actually doable. If you want to try, then yeah, that you can do. Okay. Alright, when we go to 3... Oh, wait a second, what time is it?
It's
1.
Okay, alright. So, before we move into 3D, we'll actually wait a week. So, once again, thank you very much for the attention, and this closes the lecture.